So this will be a very broad overview of volcanic seismicity, and later on we'll be introducing infrasound into the talk, and we'll be talking about why seismic and infrasound sensors are really beneficial to monitoring volcanic activity. So volcanoes are sources of great variety of seismic signals. These differ from those produced by tectonic earthquakes. Often these tectonic earthquakes and volcanic earthquakes can be a little bit hard to differentiate if they're far from the source, but seismologists are getting very good at sort of drawing out different signal characteristics which determine whether or not it's a fault failure from a tectonic earthquake, or whether it's something like magma movement from volcanic activity. Nearly every recorded volcanic eruption has been preceded by an increase in earthquake activity beneath or near the volcano, and accompanied and followed by varying levels of seismicity. And at present, there are approximately 200 or more, so about a third of active volcanoes worldwide, which are monitored by seismic stations. Of course, the number and quality of these seismic stations varies from volcano to volcano, purely based on things like funding and accessibility, of course. And then just to sort of give you the punch to this talk, for all these reasons, seismicity has become one of the most useful tools, data tools for eruption forecasting and monitoring at volcanoes. So yeah, today's talk will look at a very brief, very basic overview of earthquake seismology, sort of what that entails. The bulk of this talk will then focus on types of volcanic earthquakes, what those signals look like, and what they're mostly attributed to in volcanic processes. And then we'll look at use of infrasound to complement some of the seismic activity in volcanic monitoring. And then I'll sort of wrap up with volcanic hazard monitoring with seismic and infrasound. And that portion of the talk will largely focus on lahar monitoring, because that's what my research is in, and so it's what I know the most about. Here in these pictures, you can see, let me just hide these meeting controls. Here in this picture up here, you can see my colleagues installing a seismic station. This is at Fuego Volcano in Guatemala. And we're attaching a solar panel so that we can keep that seismic station running. And down here in the lower right, this is my colleague Scott, who is jumping up and down as we test that seismic station. So that's pretty fun. So most of us are very familiar with tectonic earthquakes. These are the ones we hear about the most in news reports and stuff. Once an earthquake occurs, the elastic waves from the fault failure travels away from the source, sort of radiates out along different paths, and then eventually reaches the surface and hits those seismometers. And the seismometers are picking up the amplitude of those elastic waves, essentially. There are several different measurements of earthquake size, but the most commonly used and probably reported is the Richter scale. So this has to do with the magnitude of these earthquakes. But you might have also heard of other types of measurements, such as the Mercalli scale, the moment magnitude, or the seismic moment. And those are just telling you different information about how destructive the earthquake was, or how large the amplitude size was, or the more technical information about velocities and stuff of these earthquakes. The major task for seismologists at that point, once it hits the seismometer, is for us to sort of be detectives and then figure out the relative contributions of the source of that earthquake. Was it tectonic? Was it volcanic? Where did it come from? Where did it start? How far did it travel? The path that it took. So that can be kind of complex, because as seismic waves move through the ground, this is, they're changing through different mediums, different rock types, different materials. And so your signals get a little bit wonky at that point. And so it takes a lot of detective sort of work to pull out some of the information about where they might come from. And then also the size effect. So how big or what was the magnitude of that earthquake? And then seismology, lastly, is also concerned with the distribution of velocities within the Earth, which many of us are probably aware of, but seismic waves have much higher velocities than what we typically deal with on a day-to-day basis, and are typically measured in kilometers per second. So these things are traveling very, very quickly. And typically when you see them on graphs such as this is not a good example because they don't have like the units on here, but typically when you see them, they've been converted to meters per second or micrometers per second in terms of their velocity. In this plot, you can see that there's two different types of earthquakes here. This is a normal earthquake or tectonic earthquake, which happened off of Kilauea in 2013. This was not from magma movement. This is from fault failure. It was a pretty shallow earthquake though. And then in the bottom here, you see more magma vibration, so more of a volcanic related activity. And as you can tell that these velocities are typically delineated in time series. So you can see that this fault failure happens within about 15-20 seconds, whereas the magma vibration is probably occurring more from 20-25 minutes here in the bottom plot. So there's a lot of information packed into these seismic signals that we can pull out and sort of to determine where exactly these signals are coming from. So active volcanoes, as I said, are a great variety of seismic signals, as you've seen in some of those plots. The generation of seismic signals in a volcanic environment particularly has been linked to a number of different processes. So in these diagrams, you can just see some examples of different types of earthquakes and where they might occur within volcanic settings. This includes fracturing of the volcanic edifice, so sort of brittle rock failure and opening of fissures and things like that. And then that movement of magmatic fluids up through those fractures. And the variety of signals is a reflection of the number of different processes that we see in these volcanic settings, and also the sort of great structural heterogeneities found within volcanic settings. So traditionally, volcanic earthquakes have been classified based on the signal's time and the frequency characteristics into 4 different types. And so we have 4 types, which are high frequency. These are more commonly known as volcano-tectonic type of signals. We have the low frequency, which are more commonly known as long period. We have explosion quakes, and then we have the volcanic tremor. And on the plot on the left here, you'll see at the top of each of these plots that we have our waveforms of our seismic signals, different forms. And then below each of those seismic signals, we have something called a seismogram, which is showing us basically the amount of energy packed into different frequencies. So on the left here of these seismograms, these are different frequencies. So in a high frequency type of signal, for this case, you would see frequencies between 1 and 10 or more hertz. Whereas in low frequency, which is in panel C here, you can see that the frequency, most of the energetics are packed within only about 1 to 3 hertz. So seismograms are really useful in determining where those frequency characteristics are and where most of the energy is being sort of partitioned into in terms of how big those waves are. let's see, in other local signals, so of course we have all of these 4 signals that we have, but then you also get hybrids, so you have both high frequency and low frequency signals sort of packed together. Within volcanic settings, again, you have to do a little bit of manipulating of your signals to sort of draw out what is visible within your waveforms. You can also have superficial processes, rock falls, lahars, pyroclastic flows that also produce seismicity. So there's a lot of signals that happen in volcanic settings. And then as we get better at determining what these signals mean and sort of facilitating our understanding of what those characteristics are, this allows greater detail in sort of our temporal and spatial understandings of seismicity to detecting a lot of these processes as well. So we'll go through each of these very briefly just to show you what they sort of look like. So the first one is volcanic tectonic. These are caused generally by shear or tensile fracturing during magma movement from depth to the Earth's surface through conduits and dikes. So they're occurring right here at the surface where the shallow magma chamber is having where the shallow magma chamber is producing some sort of magma movement, and that is sort of radiating out and creating fracturing on the volcanic edifice. The magma migration to the Earth's surface and the crustal tectonic activity are coupled so that they can pull out this information and say, oh yeah, there's magma movement. And then they have the observation of that fracturing on the volcanic edifice itself. Oh, and now my video worked.
Shallow low frequency.
Sorry, let me pause or mute that. The next one is the long period earthquakes. These are frequently characterized by emergency P waves, but unlike your high frequency, they lack S wave arrivals. It's been suggested that the occurrence of these long period waveforms is linked to either resonance of seismic energy trapped at a solid fluid interface in a crack or in a volcanic conduit. But what actually triggers these seismic data is kind of debated. People still do not fully understand why these sort of seismic signals are being produced necessarily. We know that they're shallow. We know that they usually are a good indication of impending eruption, but they don't know exactly what they're being produced from, only that they're occurring somewhere within a crack or a volcanic conduit. But some of the suggestions which have been made are that it's usually a stick slip motion along the conduit walls as magma ascends. It could be from the brittle failure of magma itself, either through an increase in viscosity and strain rates, which can occur from either the ascent rate of magma or changes in the crystal and bubble concentration in the magma, or through just a simple geometry change in the conduit. It's also been suggested, that the interaction between magmatic and hydrothermal systems could create these types of signals, or that there's a slow rupture and failure of unconsolidated material on volcanic slopes, which are producing these. With all of that said, long period signals for seismologists, volcano seismologists are very important types of, I mean, they're all very important, but these ones are specifically important because they demonstrate short-term eruption forecasting, because their timing and the vigor, the sort of magnitude of these types of signals and when they show up often accompany pressurization in our magmatic and hydrothermal systems. And so they usually indicate an impending eruption. So they're very, very important. Then we have our very long periods. So the long period signals get a little bit more complicated. In the last couple of decades, seismometers have, advanced. And so now a lot of people are using something called broadband seismometers, which have the ability to detect ground shaking over a much broader range of frequencies. And because of that, we've been able to now pull out these very long period types of signals. And yeah, so the broadband is very good at detecting frequencies across the lower frequency bands as well. So these are 120-second periods. So these are very, very long period, as they're cleverly named, types of signals. They occur again at very shallow depths, so less than 1.5 kilometers from the surface. And these are particularly associated with either the eruption itself or vigorous fumarolic activity. So like vigorous outgassing essentially from the volcano. But unlike most long periods, these have fairly small amplitudes. So and their durations again are just much longer. And then there's volcanic tremors, which are a continuous signal of duration, which is minutes to days. They can last for months. In some cases, like at Etna and Fuego, which erupt quite frequently, you see these quite consistently. And they have temporal and spectral components similar to the long period events. So the common thought here, as far as I'm aware, is that a lot of the tremor type signals are produced from a lot of the common source processes that long period signals are produced from. Moving on to explosion quakes, these typically accompany explosive eruptions. They can also accompany some effusive eruptions, depending on how vigorous those eruptions are. And these are often characterized by the presence of an air shock phase on the seismogram. I couldn't find a good example of what this looked like, but I'm sure there's some papers out there that do have good examples of what these look like. And what is happening when you get an explosion is that you get partitioning of the energy at that source. So what that means is that you can have an explosion and part of that energy is being transmitted through the ground, through ground shaking, and part of that energy is being transmitted through the atmosphere. So it's causing perturbances in the atmosphere. And two things can happen. One is that the stuff that's going through the atmosphere gets refracted or reflected and then sent back down and coupled with the ground again, so the seismometers pick it up. Or it's being picked up by infrasound. And this is where infrasound comes in and is really useful, because infrasound, which is a very low frequency, it's anything below 20 hertz, so below the human threshold of hearing, can pick up those atmospheric perturbances that are not reflected and refracted and coupled back to the ground. And infrasound also complements seismic sensors in this sort of superficial processes, these explosions really well, because it has a lot of advantages over seismic stations. They're relatively easy to deploy. Seismic stations can be a heavy burden to carry out into the field. Often you have to take like huge batteries to supply them or big solar panels to keep them going. But with infrasound sensors, some of them you can still take a lot of that stuff, solar panels and such, but there are infrasound sensors like the ones that we use that take like 2 minutes to deploy, and they're very lightweight. You can carry 5 or 10 of them in your backpack very easily out into the field. They are relatively cheaper than most seismic sensors, and also you can put infrasound sensors pretty far from the source of the energy. So I think some papers have delineated up to about 15 kilometers, 15, 20 kilometers away from the energetic source. And you will still get very good signal characteristics because they're such low frequency that their signal does not attenuate at far distances. Unlike seismic, which is much more complicated, like I said before, where it's traveling through the ground and traveling through lots of different mediums. So that signal can be attenuated greatly before it reaches the seismometer. There are some limitations to infrasound, and I'll talk a little bit about those in a second here. Lastly, we have our surficial processes. These are things like pyroclastic flows, lahars, rock slides, landslides, anything that which is happening around the volcanic edifice, lava flows, anything like that can be detected both by seismic stations and by infrasound stations. Again, I'm only going to focus on the lahar side of this, but just so you're aware, seismic and infrasound sensors can be exploited to determine sort of size and magnitude of all of these events, their location, and then their direction of flow and velocities as well. So moving into sort of the last bit of my talk here, we can use seismic and infrasound in lahar monitoring, and this is my specialty. This is the research I've been working on. So in the background here, we have fuego. It's erupting. It erupts every about 5 to 10 minutes, typically, sometimes more. You get these big sort of ash plumes. They're not huge, but it's enough to produce a lot of material and substrate on the side of the volcano. We have a time-lapse camera here that's overlooking one of the drainages. This is normal stream flow within this drainage, but every summer, this volcano produces upwards of maybe 20 to 30 lahars in every drainage around Fuego. It is there's about 7 drainages around Fuego which are active with lahars every summer. And so Fuego in itself is a very natural laboratory to study lahar processes because we know that they're going to happen. We don't know when exactly they're going to happen, but we do know that consistently we will get upwards of 20 to 30 lahars which occur around that volcano every summer. And so it makes it a very easy place to study lahars. These are rain trigger lahars, obviously, so secondary lahars as opposed to primary lahars, which are created syneruptively and from things like melting of ice and snow or crater outbreak during an eruption. And so we have deployed in a couple of different drainages around Fuego some infrasound sensors and arrays and seismic stations. On the right here, you see these are our infrasound sensors. They were built here at Boise State by Jake Anderson. These are single microphone infrasound sensors, and they're powered by D-cell batteries. Again, it takes less than 2 minutes to deploy these things. You essentially flick a switch, close them up, and deploy them. So they're very easy, and they can run up to months and months at a time, depending on the battery source. And so we generally put these about anywhere between 100 and 300 meters off the side of the drainage. Whereas our seismometers have to be relatively close to the drainage. And so seismometers actually run the risk of being damaged during a lot of lahars because the banks here on the side are very, very unstable, and these drainages undergo massive amounts of geometric change during a single lahar event and over a season. And so we're constantly having to move seismometers all the time just for that reason. So in terms of looking at how infrasound complements seismic, on the left here, this is a plot put together for one of the channels around Fuego at 2 different locations. This is an upstream location, and this is a downstream location on the bottom. This is infrasound in orange, overlaying the seismic, the vertical component of seismic in blue. And as you can see, just visually, if you look at both the signals, you can see that they follow these general patterns for both infrasound and seismic of these sort of pulses that you get in lahars. So lahars typically surge or pulse a lot, and so we can visually see those in our signals. And you can see that in terms of how discrete they are or how often they happen, that's also the same for infrasound and for seismic. And so that's good news. That tells us that infrasound is very complementary to seismic in terms of monitoring these lahars. One of the limitations of using infrasound, though, is because you're taking perturbances in the atmosphere. And because at Fuego, of course, a lot of these are happening during storm times, you're subject to a lot of storm noise in your infrasound. And that can be really, really difficult to filter out of your infrasound signals. We've tried all sorts of different types of digital signal processing with our infrasound signals, and even to the extent that which we've done it, you still get sort of these glitches, these lightning spikes. And so hopefully as technology advances, we're able to sort of get rid of some of that noise. But it can make sort of some of your calculations and stuff a little bit trickier. So at the moment, that's sort of what we're limited by with infrasound. What we do so these are your normal waveforms. What I've been doing is I've been converting those waveforms into energetics, mostly power. So on the right here, on the upper panel, I've converted the infrasound and seismic power, the waveforms into power. And I've just normalized them here in this plot to show you what is spiking, where the energetics are spiking. This is for this lower station here. And as you can see, where these sort of pulses go up and down, we still have those same sort of patterns in our powers, where energetics rise as those pulses, the fronts of those pulses are coming through. And then once you get through the tail end of those pulses, the energy sort of dies down. And our inference from that is that at the front of these pulses, you have much more of that material, that big material, because a lot of the big boulders and a lot of the heavy sediment concentration in these lahars is being pushed to the front. And so at the front of these pulses, that's where you're seeing a lot of that material and debris. Whereas at the tail end, you're seeing much more of the sort of just surface waves and turbulence, and it's a little bit more dilute at the tail ends of these lahars. We can take a ratio between the seismic and the infrasound energy, which is shown in the lower panel here. And this is maybe not the best example of this, but it's the one that I had. So by taking a ratio of partitioning of this energy, we can delineate sort of flow behaviors and where that energy is being partitioned into. So again, at the front of these pulses, you see that anything above 1 is more seismically energetic, whereas anything below 1 is more acoustically or infrasonically energetic. And so above 1, these are the fronts of those pulses, again, where those big boulders, big debris are. So you're getting a lot more interaction between boulders and the channel. So a lot more of that energy is being partitioned into the ground, where again, at the tail ends of these lahars, you're getting more acoustic energy, which means that a lot more of the surface waves and the turbulence that we see in the surface flow of these lahars is being partitioned out into the atmosphere. This is a video from another drainage called Las Lajas at Fuego. And this is sped up by like 26 times. This is a 5-hour lahar that occurred there in 2021. And this panel up here in the upper left is just showing energetics, which are these dotted lines for acoustic and seismic. And then this blue line here, the cyan line, is stage height. So I've gone through each of these videos and I've recorded, quantified all the stage height, meaning where the level of water was relative to the channel bed. And so as the time series goes on, you can see that the energetics precede the stage height, flowing past this time-lapse camera. And that's just a good way to sort of visually observe some of these flow behaviors that we're observing in the seismic and infrasound data, but also to sort of correlate, when seismic and infrasound data shows up, how much longer before stage height changes in the channel. And that is a really good proxy for how destructive a lahar can be in terms of its stage height, and also how much energy it's producing at the front of those pulses. So to sort of summarize this up, in terms of my work, is that we can use multidisciplinary data sets to qualify and quantify flow parameters with these lahars. I use it a lot to determine the timing of the lahars, the duration, the velocity, stage heights, things like that. We utilize the energy relationships to analyze characteristics within signals. And then we use time-lapse cameras to also visually observe those flow behaviors, as well as correlate them to the energetics which we're observing in our seismoacoustic signals. And the implications of this, of course, are to improve hazard forecasting and predictive hazard models so that we can implement better early warning systems for communities that live in areas which are affected by these lahars every summer. In terms of volcanic earthquake summaries, although seismic data is plentiful, the complexities of the volcanic environment often make interpretations ambiguous, so it can be very hard to delineate long periods, very long periods, tremors, until you do a lot of digital signal processing and then can pull out a lot of that information, and you have to do it in a timely manner so you know what's happening. But having said that, seismology is obviously an integral component of volcanology, and it's helped answer a lot of fundamental questions about where the magma is, what is normal or background activity or tectonic activity at volcanoes, and what will happen next or what will happen in the future. Because often, like I said, you get an increase in earthquake activity right before an eruption, and a lot of papers, a lot of seismologists are looking into patterns that they see at particular volcanoes, and what those patterns are telling us about what the volcano is doing. But then again, seismology alone may be somewhat of a limited tool, but we can use complementary tools like infrasound and time-lapse camera to facilitate our understanding of volcanic processes, especially at the surface. So that is it for my talk. I'd like to thank everyone. And yeah, if you have any questions or would like to get in contact with me, feel free to email me. So thank you.